So, we're just going to be naming some facts for fluids in motion. If a fluid in a system has no source providing additional fluid or sinking or draining off the fluid, the volume of the fluid entering must what? Must match, yes, must be equal to the volume of fluid flowing out. All right. In other words, if we look at this picture below, we have this pipe where the fluid is flowing into the system. Well, an equal amount of fluid has to be flowing out of the system if it's full. We know this because density, what is density? Is mass over volume. Or we could say that mass is equal to density times volume. And it's really just an expression of the conservation of matter, right? We have the same amount of matter flowing into the system, so that the change in the volume here is equal to the change in volume here. Thank you so much. Tovar. But we also know that this could be the same, not just volume, but the same mass. So we could say that it's the same rho v. I should say delta v. That's also mass. All right. All right, so another important result about incompressible fluids is called the continuity equation. The volume that passes a certain point in a given amount of time is equal. That the cross-sectional area of the pipe and the velocity are what kind of proportion then? If it gets a smaller cross-sectional area, that the speed has to do what? It has to speed up. So fluids flow faster through narrow pipes. This makes sense because if we just have a simple bottleneck, like a plastic ketchup bottle or a mustard bottle, that the little nozzle allows us to apply it in a faster way than just moving it across in the regular bottle section of it. We know that the flow rate in equals the flow rate out. That we have volume 1 per period of time equaling volume 2 per period of time. But we're going to split our volume into more than one parts. What is volume if we gave a physical measurement of it? What times what times what? Length times width times height. So what if I just separate it into this cross-sectional area by the length which the cross-sectional area travels? That's also the volume, right? We have width and depth versus the length that it travels. And so we could have this area as it travels down the tube. Well, that's a volume. And we're going to take the volume per time, right? So, actually, let's just put it here. A-L over T. A1L1 over T equals A2L2 over the same time period. Okay. But then, what do you know about a length over time? What's L over T equal? Velocity. When I type velocities, or when I write velocities in this unit, I'm going to put an arrow over them. Does that help? Why? Because it's not going to be volume. Okay, this is going to be the vector velocity. So here we have area times, and that wouldn't make sense if it was volume, because area is 2 of the 3 dimensions of volume. Well, we use that last one, and we can say area times velocity equals area times velocity. Area 1 versus area 2. Velocity 1 versus velocity 2. Which makes sense because fluids flow faster through narrow pipes. This is just the equation for it. Okay. If we have a smaller cross-sectional area, the speed would go up to counteract that. If we have a larger cross-sectional area, you don't have to flow as fast. This is the same for things like if you wanted the flow to be the same for freeway traffic. It's just that that's not how cars work, right? They get to choose their own speed. This is, however, how garden hoses work. Okay. So if you've ever seen a garden hose, what can you do to get it to go and flow faster? Yeah, you could just cover the end. Your hose might have different nozzle styles at the tip of it. And so the smaller ending, the faster it will go. Or sometimes we have things like watering cans style nozzles to spread out all the water and distribute it out so it flows wide and softer. Okay. Pressure washers. Oh, that's interesting. Pressure washers actually have very small cross-sectional areas to shoot water very fast, right? Because if you've ever watched a pressure washer, or if you've ever seen the results of a pressure washer, the water that trickles down the driveway is actually oftentimes less than just letting a hose run. It's a very small amount of water being shot very fast because we are directing it out of a small nozzle. Shallow and narrow rivers versus deep and wide. What are the biggest rivers in the world? The Nile. And which one's bigger than the Nile? Amazon. Okay. Which one's which? They have different greatness ratings. Which one's greater in what? What's the longest river? The Nile is narrow, but it's the biggest one. And deep and wide, that can have a lot of volume, is the most voluminous is the Amazon, right? But if you watch the rate of flow of the Amazon, it's not very fast. It holds a lot of water. It doesn't flow a lot of water. Okay? Ideal liquids also obey special statements of conservation of energy, which is Daniel Bernoulli. (1738). All right. So Bernoulli's principle. Where velocity of fluids is high, the pressure is low. And where the velocity is low, the pressure then would be high. Okay. Bernoulli's equation is an expression of the law of the conservation of we already saw the conservation of matter. This one's the conservation of energy. Okay. So for these diagrams, we're just going to label something that if it moves a length here, if these were the same size, it would move the same length, right? And if it's different sizes, they would have to move different lengths. We know that pressure is what? Over what?
Force over area.
And so for these to move, for the liquid inside to move, we might be worried about force being pressure times area. Same equation, just rearranged. Well, now we have work being done. Because what ends up happening is we've got a force moving a distance. We just called it different things. In our case, the work that we're talking about, the work that we're finding, comes from a force, which is pressure times area. And the distance that we're worried about is L, the length that it travels down the pipe, right? It's just a different letter for the distance that it's traveling, though, right? That's not crazy. Okay. On the other end of things, especially if we're changing the size of the pipe, if we have a large section, the large section would have a large area, right? So if we have a bigger area, that means what? Is it moving fast or slow?
Slow.
Okay, so speed goes down. Which means, what could you tell me about energy for kinetic energy?
Goes down.
Kinetic energy is based on the speed. But we have high pressure. Let me write that. High pressure. In the skinnier cross-sectional area, when the area goes down, what do you notice? What happens to speed?
Speed will increase.
Speed increases, and that means kinetic energy also increases. This is a low pressure area. Okay. So this is what ends up happening when a fluid flows through a small cross-sectional area. To conserve total energy, it loses pressure. Because remember, pressure is part of the work. Okay? So if work is being done for it to move fast, it uses that energy in terms of work energy. Again, this is the total pressure. So let's read it. A force F1 pushing on piston 1, moving it with a constant velocity V1, results in piston 2 moving to the right at speed V2. So the pressure in this equation is the total pressure. We're talking about energy. So what do we need to do if we're talking about the conservation of energy? Yep, the total energy initial equals the total energy final. And for all of ours, we're going to split it up into 3 different parts. We have work being done. We have kinetic energy. And what is it trying to allude to with this picture? What other kind of energy do I have? Gravitational potential energy? Initial will equal the work out plus kinetic final plus potential energy final. What letters did we give work for this unit? Work is our PAL. P-A-L. Kinetic energy. What's we know this. 1/2 what?
mv squared.
1/2 mv squared. UG is simply just mgh. Will equal same equation, PAL plus 1/2 mv squared plus mgh. Let me go back and say, okay, at the beginning, the pressure, area, and length, those all have an individual piece. M doesn't change, but V, that's the speed, right? I should put an arrow over that. The speed is only good for 1, and the height is only good for 1, even if the mass is the same. So let me put 2, 2, 2. 2 for the velocity, 2 for the height. For the other part, if it doesn't have a number by it, it probably stayed the same from both sides, or it's the same amount of mass. All right. Well, doesn't look like very much could cancel out unless rho v. What's rho v equal? Unless rho v equals mass? Okay. Because I could actually say, oh, there it is. There's the ideal gas law. PV plus, oh, why is PV on one side of the equation? That's an interesting idea. Plus 1/2 rho v, right? That's mass, velocity squared, plus rho v gh equals PV plus 1/2 rho v squared plus rho v gh. In this, let's keep the numbers. 1, 1. Mass is the same. Velocity is for 1. Height is for 1. 2, 2. 2 and 2. And let me put parentheses around this just so we know this was our mass value. Wait, what did we say about the mass value? It didn't change, right? What else doesn't change? The what? The volume. So not only do I get rid of the V1 versus V2, the volume stays the same, but that means what cancels out across the entirety of the whole equation? Right. The volume goes away. So really we're just left with pressure at 1 plus 1/2 rho v velocity squared plus rho gh equals P2 plus 1/2 rho v squared, that's a velocity, plus rho gh. We have this almost like a pressure conservation, but pressure from your different energy sources, right? Because we have pressure from work, we've got pressure from kinetic energy, we have pressure from potential energy. We'll equal our pressure from work being completed versus pressure from kinetic energy and pressure from the potential energy. So Bernoulli's equation can be written as P plus 1/2 rho v squared plus rho gh is a constant. For a fluid, for a pipe system, whatever happens. As long as we're in the same medium and the same general spacing. So, this is how we generalize airplane wings, which there's a lot going on with airplanes these days. There's more than just Bernoulli's principle, but that's how we get lift. Spoilers on cars, curvatures of the baseball going around. We could create a vacuum that helps, kind of like this atomizer idea that we'll talk about, that a vacuum can be created by flowing water. That's how we used to create vacuums in classrooms to help speed up. Did y'all do this? No, y'all have just vacuum outlets on the walls, but to help speed up drying out processes, you filter through paper and then you can help dry it out with a vacuum, suctioning all the liquid down. Atomizers, if you squeeze, there's a low pressure which sucks up the liquid. All right. So that's Bernoulli's principle in a nutshell.